Assalamu alaikum to you all. So in the last lecture we discussed about singly linked list. In this one we are going to study the next data structure which is called doubly linked list. The outline is as follows. As usual, we will explain what is the term doubly linked list. And then we take a little motivation about why we want to study this particular data structure. And then we will go deep into the implementation. How do we implement doubly linked list? Looking at processes like insertion, deletion, and so on, like we did for the singly linked list. In the second part of the lecture, we will look at the lists that are available in the Java library, particularly linked list and array list. I'm sure you have come across this in your programming 2 course. So this is more like a revision. Okay, so let's start with the doubly linked list. What is the motivation for wanting to study it, having already studied how to implement singly linked list? Well, as you might have noticed, some of the methods of singly linked list were not very efficient. For example, the delete from tail method, if you recall, it required us to use a loop starting from the beginning of the list until we reach the second to the last node, simply because we want to delete the last node. Okay, and the main issue here is we don't have a reference to the previous node, because actually to delete the last node you need the reference to the node just before it. If we had prev reference, then the last node, which we can access through the tail reference, can also tell us which node is the second last. Unfortunately, we didn't have that in singly linked list, and therefore, as we said here, that nodes in such list contain no references to their predecessors, and for that reason we had to scan the entire list to find the predecessor to the last node, which we need to delete the last node. This scanning process, or looping if you like, definitely makes this method inefficient, especially if the list is very long. Imagine if you have a list containing 1000 nodes, and just to delete the last node you have to traverse 999 nodes, because you have to start from the head, next, and so on until you reach the second last node before you can actually delete the last node. So obviously this is not efficient. So for this and similar problems, we need another modification, and that is in the form of doubly linked list. Okay, so doubly linked list is going to solve this problem for us. That is basically the reason why we want to study it. So what is a doubly linked list? A doubly linked list, as I think we mentioned briefly when we were defining link structure and then linked list and then singly linked list, is a linked list in which each node, in addition to the data element, it has 2 reference fields, one to the successor node and one to the predecessor node. Okay, this diagram shows how a doubly linked list looks like. So each node, in addition to the data element, will have not just next reference but also prev reference. Of course, the first node has no prev, so usually its prev reference will be null. just like the last node has no next, so its next reference will be null. But otherwise, most nodes will have two references, one to the successor and one to the predecessor node. Okay, so this is the idea of doubly linked list. Now, before we proceed, can you imagine any disadvantage for doubly linked list, at least comparing it with a singly linked list? We're going to see that it's going to give us more efficient methods, particularly the delete from tail is going to be more efficient now because we don't need that loop to be able to delete the last node. But is there any particular disadvantage? And remember, as I emphasized in the last lecture, when we are talking about advantage or disadvantage, our main concern really is with respect to time and space, or speed and memory. So can you imagine any disadvantage of doubly linked lists comparing it with singly linked lists with respect to these two particular points? It is obvious if you can look at the node. Each node in the doubly linked list has now three variables, not just two: info, pre-annexed, and prev. In singly, we only had two: info and next, info and next, info and next. So obviously, in terms of memory, doubly linked list is gonna take more memory compared to singly because of the addition of this extra variable. So that is the main disadvantage. It takes more memory compared to singly, but it gives you faster operations. This is usually how things are actually in data structure. You hardly get a data structure that is 100% always perfect. No, it's usually give and take. Okay, so this gives you faster operations, but at the expense of using more memory. Okay, so that's basically what is a doubly linked list. Now let's go into its implementation. And as we did for singly linked list, the first step is to implement the node class. Okay, we want to implement a node class representing the node of a doubly linked list. And this is the class heading. So we call it DLL node, whereas this is the one for the singly, we call it SLL node. Okay. The main difference actually is here. In singly, we had only two variables: info, which is of generic type T, and next, which is of type the same node. So, but here we're going to have not only next, but also prev. So we have two references referring to the data type of the same class, which is DLL node. Okay, so the type of these two variables, next and prev, is DLL node. And as we saw in the figure in the last slide, this is how a DLL node looks like. It has three fields: info, next, and prev. So if you create an object of this class, this is what will be allocated for you: three variables in the memory to store the information for a node. Okay, what about the constructors? Again, we will start with the last constructor, which is the main one. Here, the assumption is we're going to receive arguments for all the three variables. So as you can see, we receive element of type T, we receive n of type node, DLL node, and p of type DLL node. What do we do with these three arguments? We use them to initialize our instance variables. So you can see info becomes element, next becomes n, and prev becomes P. This is essentially what constructors do always. Initialize the instance variables. Okay, we have another constructor which assumes we don't have information for the next and prev. We only have the information for the info field. So in that case, how do we initialize our node after we create it? Simply by assigning the info to the info field. So you can see here info, it becomes element, but the other two variables will be assigned null value. Okay, null values. Okay, so here contrary to what we did with singly, we are doing the assignment directly in the constructor itself. The other option, of course, is to call this constructor. So we could have said this, and then we pass the three arguments: element, null, null, and allow this last constructor to do the assignment for us. But we have decided to do it directly here, just to show you, the two options. You can choose whichever you like. The last constructor is, as before, assuming we don't have any input. So the constructor here will just set the two variables here to null. In fact, there is really no need, because if you don't initialize an object like info, next, and prev, if you don't give it a specific value, automatically it will be null anyway. Okay, so this is what this first constructor is doing. So this is our DLL node class. There is no method at all inside the class, just like the singly linked list node. Now at this point, if you wish, you can now try to see whether we can create a doubly linked list using only the DLL node class, as we did for the singly linked list node. But really there is no need, because we know it is not going to be practical anyway. So in fact we need a class which will allow us to manage the nodes in our doubly linked list. Therefore, we define another class which is called DLL. So instead of SLL, this one we call it DLL. Now DLL, like SLL, has two variables, head and tail. The idea is exactly the same. We want head to help us reference the first node in the list, and tail to reference the last node in the list. Okay. The constructor of the class simply initializes both head and tail to null. Okay, there is nothing more to explain. It's exactly as we did with singly linked list. The only difference here is we are using a different name. This is DLL, and the node is DLL node. Okay, this is empty. Again, the list will be empty if head is null. If you wish, you can also say if tail is null, because actually if the list is empty, both head and tail are null. But there is no need to check for both. Just checking one of them is enough. So to implement this empty, we just say return the result of this comparison. Is head equal null? If yes, return the true. Otherwise, return false. Okay. Another easy method we can implement right away is clear method. The clear method is expected to empty the list. So assuming the list has already been populated with a number of nodes and we want to empty it, you don't have to call delete and delete from head, delete from, and so on until the list becomes empty. No, just simply say head becomes tail becomes null. Once head and tail are both null, all the nodes Starting from the first one will have no reference, so it will be deleted. Then the next one will have no reference, it will be deleted, and so on like that. So gradually all of them will be deleted. So there is really no need to go and individually delete the the nodes one by one. Just setting head and tail both to null will delete the list automatically. Okay. One more method. Suppose we want to access the info inside the first node. This is what the get first method is doing. Get first, as you can see, the return type is T. It's simply saying give me the information in the first node. So here head is already pointing to the first node. So if you want the info, all you have to say is return head.info. However, you have to be careful. The list could be empty. If the list is empty, head is actually null. So if you say at that point head.info, you're going to get a null pointer exception. Okay, so it's good therefore before you return head.info to check if head is not null, so the list has some nodes, then return head.info. Otherwise the list is empty, so simply return null. This is basically what the get first is doing. I'm sure you can imagine how you will be able to do get last. Okay, this is one of the exercises you will do in the lab. Okay, now let's go to the more interesting methods of insertion, and then after that deletion. Starting with add to head. So add to head is very similar to add to head of singly linked list. The only difference here is we have two references, not only next but also prev. So in our assignment, we have to make sure we assign the correct values for each of the two variables. Okay. Now, like in singly, we have two scenarios. We could have a situation where the list is empty and a situation where the list is not empty. It already has some nodes. So the way we implement the method therefore depends on those two scenarios. Okay, so we're going to take the easy one first. It says here if head is not null, we will do this. So we're going to skip this for a moment, else do this. Okay, so this is the case that will be executed in case the list currently is empty. And to explain that code as we did in singly, let's look at the diagram. So our head is null and tail is null. The first thing being done here, remember we always explain assignment statement starting from the right, because that's how it will execute. It will execute this, then assign it to this, then to this. Okay, so we're going to look at this one first. If you say new, remember new, create an object. What type of object? In this case, object of type DLL node. So this is the object that we're going to get. DLL node object will have three variables: info, next, and prev. So that's what we have. Next step, the constructor will be called, giving it some information. The information that the user will pass when he calls the add to head. So for example, he say add to head 6. So element here, let's say, is 6. So what will happen? The constructor will execute. Which of the constructors? Obviously the middle one, because it is the middle one that is expecting only one argument. Okay, and if you recall, the middle constructor will assign this value to info, and it will assign next to be null and also prev to be null. So after executing the constructor, this is what you have. So here we are assuming element actually is past 3. So the user sent the number 3 to be added at the beginning of the list. So 3 will be assigned to the info, and next will be null, and prev will be null. So this part of the statement is done. Next is the assignment itself. Remember, new will return the address of the object that has just been created and initialized. So that address, we are saying assign it to tel. So tel is not going to be null anymore, it's going to point to the node. And then after that, send the content of tel also to head. So head becomes whatever is in tel. Well, what is in tel is the address of this node. And therefore, head will also cease to be null. Instead, it will be containing the address of the node. So this is what these two assignments will do. Okay, both head and tel will contain the address of this object. Okay, they will point to the object. This is how we show it diagrammatically. And this is what this method add to head will do in case the list is empty. The second scenario is where the list is not empty. So suppose, for example, we have a list containing 3 nodes, 6, 5, and 8. And presently head is pointing to this node and tail is pointing to this one. We want to add a new node at the beginning of the list. So how are these two statements doing that? Let's start with the first one. It says head becomes new DLL node, element head null. Okay, so again, let's look at the right hand side of this assignment statement first. New will create a new node. Okay, then the constructor will be called. Now here, notice we are passing 3 arguments to the constructor. What does that mean? It means we are calling the last constructor, the one that is expecting 3 arguments. So we are saying go and send into info the value of element. So assuming element is 3, then 3 will be saved in the info of our new node. Okay, and then we say save in the next of our new node. This, the middle variable here is next. Store in it the same as the content of head. Well, head right now is pointing to this node. So the content of head is the address of this node. So we are saying store in this variable the address of the same node. And therefore, next will point to that node, just like head. Okay. And finally, store in the prev, because if you remember, the last parameter is to be assigned to prev. So we are saying save in prev null. Okay, so essentially this is what will happen. Okay, our node will have 3 in its info, address of this node in its next, and null in its prev. This is what the constructor will do. Okay, so we are done with the right hand side. We're going to receive the address of this node. What do we want to do with it? It says assign it to head. Head becomes the address of the new node. See, head right now is containing the address of this node. So we want to change it. Let it be the address of the new node. This is what this assignment is doing. Okay, so that is what you have right now. So head is no longer here, it is here, pointing to the new node. Now, but we are not done yet. If you look at the list, is not yet complete in terms of doubly linked list, because you see the prev of this node is still null. We want the prev to come to the new node. Okay, so this is the difference between singly and doubly. In singly, this was only what we had to do, but now with doubly we have to add one more assignment. Okay, so how do we do that? First of all, how do we reach this variable? Okay, starting from head, we reach it by saying head dot next dot prev. Okay, so because before we can change it, we need to access it. So to access it, we have to say head dot next dot prev becomes what? Becomes this node. So which reference is pointing to the node right now? Is head. Head is pointing to that node. Therefore, this variable becomes the same like head. It should point to the new node. Okay, this is exactly what we have here. Head dot next dot prev becomes head. Okay, this is what that means diagrammatically. So that variable, which presently is null, will not be null anymore. It's going to point to the new node, just like the head is pointing to the new node. Okay, I hope this is clear. Okay, this variable, to access it, you have to say head dot next dot prev. Then you will assign to it the address of this node. Right now, head is the only variable that we have containing the address of this node. So therefore, we assign head to that variable, and the link is complete now. This is the explanation for the add to head method. Let us look at now the add to tail method. So again, there are two scenarios. The list could be empty, and the list could have elements already. For the empty, there is no difference with the add to head. Okay, we simply create a new node, a new DLL node, that is, put the info here, and make both head and tail to point to it, exactly like we did in the add to head. No difference if the list is empty. Just create a new node and make it to be both the first and the last node. The difference is if the list already has some nodes, like here. So suppose we have a list, again, containing 3 nodes, 6, 5, and 8. And now we want to add a new node at the end. Okay, so the first thing to do is to create the node. And therefore, you can see here we say new DLL node. Okay, then we call the appropriate constructor to initialize it. Okay, so here we are passing element, null, and tail. Let us see why. Obviously, the element, whatever the value is, will go to the info part. But the second argument, if you remember, is to be assigned to next. But this is going to be the last node, and last node, normally they don't have next. Okay, so next should be null. Okay, and the last parameter here is supposed to be assigned to prev. So which node is going to be the prev of this one? It is this one. And what variable do we have right now that is pointing to this node? It is tail. Therefore, we're going to say assign tail to this variable, so that this variable will point to the same node. This is basically what the constructor is going to do, as you can see in this B part of the diagram. So assuming we are inserting 10, so 10 will go to the info. Okay, null will go to the next, and tail will go to the prev. Okay, so prev will and tail will point to the same node. That's what we mean. Okay, tail is currently pointing to this node. So if we say this become tail, we are saying this goes to the same node as tail. Okay, great. Now, having done this link, we now want to update our tail, because tail should not be this node anymore. It should be this one. This is the new last node. So, and we remember when we say the result of new, we're going to receive the address of the node that has just been created. So we are saying assign it to tail. So tail will change. It's not going to point to this node anymore. It's going to point to this other node. So tail will be here. Okay. Are we done yet? Actually, not yet. Because if you look closely, there is still one more link to deal with. Again, this is the difference between singly and doubly. The next of this node, the previous last node, is still null. We want it to point to the new last node. So we need another statement to do that. And the first question is, how do we reach this variable? Okay, we have to say tail dot prev dot next. Okay, so this is how to reach this variable. And what we want to assign to it, we want it to come to this node. So which reference is already pointing to this node? It is tail. Therefore, we will assign to this variable the value of tail. This is exactly what this second statement is doing. Say tail dot prev dot next becomes tail. Okay, so this is the final diagram, therefore, after doing the second statement. And you can see now our doubly linked list is complete with the new node added, with all the references assigned to their correct nodes or correct values. Okay, so this is about adding a node at the beginning and adding a node at the end. I may ask you to do adding a node in the middle in the lab. Okay, let's move now to deleting a node. So we're going to look at the two options, delete from head and also delete from tail. But starting from delete from head, like we saw in singly, there are three scenarios. The list could be empty, and the list could have only one node, or the list could have some nodes, more than one node. Yani. So we have to treat each case separately. There is no difference, or with singly in terms of the first two scenarios. If the list is empty, just return null, nothing more. Okay. If it is not empty, the first thing to do is to save the info in the head node. Okay, so we define a variable here, element, and save in it head.info before we try to delete the node. Now, deleting the node, it depends. If it is the only one, then again there is no difference with what we did with singly. Simply empty the list by setting head to be equal to tail to be equal to null. At this point, actually, if you wish, you can say clear. You can call the clear method to do it. Okay, because this is exactly what clear will do. Okay, but otherwise, what do we do? Okay, so I should have been showing you the diagram. They are exactly as we saw in singly, nothing much. If it's empty, nothing to do. If it is only one node, just set both head and tail to be null. Okay, the third case is where we have some nodes already and we still want to delete this first node. Okay, so let's look at the two statements in this else part. It says head becomes head.next. If I recall, this was the only thing we had to do in singly linked list. Move head to the next node. So head becomes head.next. So head will point to this node instead. Okay. In singly, that's enough because the node here then will have no reference. But if you look, this node, even if we move head to here, it still has a reference. This reference is pointing to that node. So it's not going to be deleted yet. So the question is, how do we break this link? Okay, now by the time head come here, as you can see in this diagram, okay, so this first statement just move head to become head.next. So head will be here. We still have to break this link. The question is, how do we reach this link? We need to set it to be null, but how do we reach it? It is simply head.prev. Remember, this is head.info, head.next, head.prev. So we just need to set head.prev to be equal to null to break this link. And that is what we are doing here. Head.prev becomes null. Okay, so if you do that, this is what we have. And you can see at this point, this node has no reference pointing to it. Okay, and therefore it's going to be automatically garbage collected or deleted. So this is the delete from head. Delete from tail is very similar. I will go over it quickly. Again, we have the three scenarios. It's empty, it's only one node, and it's more than one node. For it's empty, there is nothing to do, other than just returning null, just like delete from head. Similarly, if the list has only one node where head is equal to tail, again there is nothing to do other than emptying the list. So head equal to tail equal to null. Okay, so the node will have no reference, it will be garbage collected. The third scenario is the one we have to be careful. So we have nodes already in the list, and we are interested in deleting this last node. Okay, so how do we do it? It says first bring the tail back by one node, and the way to do that is tail becomes tail.prev. Okay, tail is pointing here. Tail.prev is this reference, tail.prev. We want tail to come to the same node, therefore we will say tail becomes tail.prev. So if you do that, tail will point to this node. Okay, now we need to break this link, because if we can do that, then this node will have no reference, so it will be garbage collected. The question is, how do we reach this link? It is simply tail.next. Remember, tail.prev, tail.info. So all we have to do is to say tail.next becomes null. And that's exactly what the second line is doing. Tail.next becomes null. Okay, so if you do that, null will be put in that variable, and that means this object has no reference, so it will automatically be deleted, and that will result in having our list containing now only 3 nodes, with the last node being deleted. This is basically how delete from tail will work. Print all is exactly as we saw in Doubly, rather in singly linked list. There is no difference. Other than that, of course, the node has to be of type doubly linked list node. Wherever you define a temp variable, it should be of type DLL node, not SSL node. Other than that, the method is exactly the same. Okay, we just need to define temp initially pointing to the first node. Then we print temp.info. and then move temp to the next. Okay, this is what this loop is doing. So initialize temp to head, and then as long as temp is not null, print temp.info, and then move temp to the next. Okay, so initially temp will be pointed to the first node. We will print the 6, then update temp to temp.next, so it will point to the second node, print temp.info, which is 5, and so on and so forth. By the time we print the 10 in the last node, and we say temp becomes temp.next, well, temp.next is null. Okay, so it will be something like this, and you can see now our condition will be false, so the loop will stop. Okay, so there is no difference in this method compared to the same method that we saw for singly linked list. Similarly, find is equally the same. The same like one in singly. The only difference is that when you are defining temp, it should be of type DLL node, not SLL node. So if you recall, the idea of find is you give a certain key, and it will go through the list to find a matching node, the node whose info matches the key that you give, and it will return to you that one. Of course, if it is not found and you have reached the end of the list, then you will return null. Okay, so we define a temp variable, initialize it to head, and the condition for repeating the loop is as long as temp is not null, we have not reached the end of the list, and temp.info is not equal to our target element. So as long as both of these are true, just move to the next node. So we keep moving until we find a matching node, or until we reach the end. And therefore, when the loop stops, and the loop actually stops, as you can see, it doesn't have any body, just the increment. So when the loop stops, we just need to check what is the value of temp. If it is null, it means we never find our target, and therefore just return null. But if it is not, then temp will have stopped at the correct node. So just return temp.info. Okay, this is the find method, nothing different from the one in singly. And the last method is also more or less the same. The general delete method, the one that takes an argument and try to find the node containing this information and deleting it. Most of it is the same like singly, but there is a slight difference in the else part here, the typical case. Okay, but before we look at it, let's look at the 3 initial trivial cases. First one is saying if it's empty, of course there is nothing to do, just return null. Okay, second case is the target could be in the first node. Okay, how do we know that? By saying if head.info equals our target. So if that is the case, it means we want to delete the first node, and we already have a method that can do that, is delete from head. So just say return the result of calling delete from head. Similarly, if the target is in the last node, just return the result of calling delete from tail. Okay, now if none of these 3 cases is the case, what it means is our target could be somewhere in the middle of the list. So we have to traverse the list from the beginning to try and locate it. Okay, now this is where the difference comes, comparing this method with the one in singly. If you recall, the one in singly, we had to actually use 2 references, pred and temp, so that when we reach the correct node, we can do the deletion by saying pred.next becomes temp.next. But here, because it is doubly, we don't really need to go with 2 variables. one variable is enough. So that's why here we have just temp. No need for print. Okay. And the first value of temp, of course, is head.next, because we are sure our target is not in the first node. Okay. So initialize temp to head.next. What is the condition for repeating the loop? As long as temp is not null and temp.info is not equal to our target. Okay. There is nothing to do in the body, so there's no body for the loop, but the increment is just like the one we saw in singly. Simply move temp to the next node. Okay. So temp will keep moving until either it reaches the end of the list, at which time it will be null, or until it is pointing to our target. Therefore, after this loop, we need to check what is the condition of temp. If it is not null, then we have a scenario like this. Let us say in this list, we are trying to delete the node containing 9. So element is 9. Okay. So we start from the beginning, we keep going until we find a node whose info, see here, temp.info, is equal to our target 9. So temp will, by the time the loop stops, temp will be pointing to this node. The question is, how can we delete this node with only temp? In the singly, if you remember, we had prev here. So we say prev.next becomes temp.next. But this time there is no prev. But also because it is doubly linked list, we also want this guy to jump and point to this node. So there are two assignments actually we have to do. Okay, so let's start with this one. Okay, always when you are trying to do an assignment, you have to identify what is it that you want to change. That should be to the left side of the assignment. And what value do you want to assign to it? What new value do you want to assign to it? That is the one that should be on the right. So this is the guy we want to change in our first statement. The question is, what is it? How do we reach it? We have to say temp.prev.next. So temp.prev.next. This is the one we want to change. What do we want to change it to? We want to change it to this one because we want it to come directly to point to this node. And this is the only reference right now that is pointing to this node. So what is this reference? You can see this reference is simply temp.next. Temp.next. So we're going to assign that variable to be temp.next. Okay, essentially we're going to do this blue arrow, if you like. Instead of the next of this node coming here, no, it will jump and come directly here. Okay, but this is only half of the story, because this node, we want its prev to jump this node and come to this node. So the question is, how do we reach its prev? How do we reach the prev of this node, given that we only have temp? Well, we have to say temp.next.prev. Okay, this will take us here. So that's what we have here, temp.next.prev. Okay, this is the one we want to change, so it should be on the left side of our assignment. What new value do you want it to become? We want it to point to this node. And the reference to that node is this variable here. So what is this variable? It is simply temp.prev. So we will assign temp.prev to that variable. And by the time you do this, you will see that this node now has no reference, because previously it has two references, this one which we killed and this one which we have also killed. So it now has only temp, but temp is temporary variable. Once we leave the method, temp will not also be there, because temp is a local variable. So the node will eventually be garbage collected. But before it is garbage collected, we want to return the info inside it. So this is what this last statement is doing. It's saying return temp.info. So return the 9. Okay. And then once you exit the method, then the node will have no reference, and therefore it will be garbage collected. Of course, if the loop stops because temp is null, it means we didn't find the target, and therefore just return null. This is basically the delete method, and that is the end of the method that we will discuss. We will see more methods which you will be asked to do in the lab concerning our doubly linked list.